There is a piece of steel on every freight car in the world that almost nobody thinks about. It is roughly the size of a human head, it weighs about 80 pounds, and it is the only thing holding one car to the next. Railroaders call it the knuckle. Every ton of pulling force in a train has to pass through it, one knuckle at a time, all the way down the line. Now stretch that line out to 4.5 miles, 682 loaded wagons, nearly 100,000 tons of iron ore, and a single person in the front cab, holding a throttle that commands all of it. That train ran. It ran on a June morning in 2001 across the red dirt of northwestern Australia, and it is still the longest and heaviest train ever assembled. But the record is the least interesting thing about it. The interesting question is the one nobody asks. Why has the United States, with the largest and most sophisticated freight rail network on the planet, never come close? And more to the point, why will it never even try? The answer has almost nothing to do with locomotives. It has to do with what surrounds the track. Start with the physics, because the physics is where every conversation about train length begins and, in America, where it usually ends. A train is not a rigid object. It is a chain of separate masses, each one connected to its neighbor through a coupler with a small amount of play built into it. That play matters. Without it, a locomotive could never get a heavy train moving, because it would have to break the inertia of every car simultaneously. With it, the engine takes up the slack car by car, snatching each one into motion a fraction of a second after the one ahead. Railroaders call that slack action, and on a short train, it is a gentle shudder you feel in the caboose. On a long one, it becomes a wave. The chain stretches when you pull, called draft. It compresses when you brake, called buff. And those two states travel down the train at their own pace, meeting each other, canceling, amplifying. Get it wrong, and the consequences are immediate. A draft force spike snaps a knuckle and the train breaks in two. A buff force spike on a curve shoves the car sideways against the rail, and a lightly loaded car in the middle of a heavy train can be squeezed straight off the track. Engineers call it string lining, and it looks exactly like what happens when you push a piece of string across a table. So the first constraint on train length is not power, it is force management. And the way you manage force is by not concentrating it at the front. That is what the 2001 record run actually demonstrated. The 8 locomotives were not lined up on the head end like horses in a harness. They were spread through the consist, spaced along nearly 5 miles of wagons, each one taking commands by radio from the lead cab. The load was shared. No single coupler anywhere in that chain ever had to carry the pull of the whole train behind it. That technique is not Australian. It is used across North America every day. So distributed power alone does not explain the gap. Here is what does. Every one of those 682 wagons was identical. Same design, same tare weight, loaded with the same commodity to the same tonnage, sitting on the same trucks. A train like that behaves like a single predictable object. The engineer knows exactly how it will stretch, exactly how it will bunch, exactly how the brake application will propagate from front to back, because every segment responds the same way as every other segment. Now picture the alternative. A mile-long train where car 12 is an empty flat car, car 13 is a loaded tank of liquid that sloshes forward every time the brakes come on, car 14 is a stack of intermodal containers riding high and light, and car 15 is a covered hopper at maximum gross weight. Every one of those cars has a different mass, a different center of gravity, a different response to slack. The forces do not cancel neatly. They pile up in unpredictable places. That is not a hypothetical. That is a normal American manifest freight, and it is the reason a train that would be routine in the Pilbara is genuinely dangerous in Ohio. Which brings us to the second constraint, and the one that really settles the argument. Not the train. The railroad underneath it. The iron ore lines of northwestern Australia are among the youngest heavy railways on Earth. The first of them went into service in the mid-1960s, laid across country that had almost nothing on it. No towns to route around, no farms to buy out, no existing rail alignment inherited from a company that went bankrupt in the 1880s. The engineers who surveyed those routes were handed something almost no railway builder in history has ever been given: a blank page and a single instruction. Move ore from that mine to that harbor as cheaply as possible, forever. Everything about the resulting railroad follows from that instruction. The rail is heavier than almost anything used in general freight service because it only ever has to carry one kind of load, and that load is enormous. The sleepers underneath it are concrete, spaced to handle axle weights that would flatten a conventional main line. The curves are broad and lazy because there was nothing to curve around, and gentle curves mean lower lateral forces, which means longer trains are safe on them. The passing loops where opposing trains wait for one another were built long, not to some inherited 19th century standard, but to the length of the trains that were actually going to use them. And the grade crossings simply do not exist in any meaningful number. A train out there can run for hundreds of kilometers without meeting a public road at track level. There is no school bus, there is no ambulance, there is no farmer waiting at a gate with a tractor and a trailer full of hay. Read that list again and notice something. Not one item on it is a technology. They are all decisions. Decisions made once, at the beginning, by people who knew exactly what the railway would carry for the next 50 years. That is the real Australian advantage. Not better engineering, total certainty about the future. It also explains why anyone would want a 4-mile train in the first place. When your entire business is measured in cost per ton delivered to a ship, every wagon you add to an existing train is nearly free. The locomotives are already running. The driver is already paid. Stretch the consist, and you spread all of those fixed costs across more cargo, and you cut the number of trips you have to make in a year. The executive who oversaw the record run put the reasoning plainly at the time. If you never push a system past what you think it can do, you never find out what it can actually do. That train was a controlled experiment, run over a stretch of the ordinary route, and it was ended once the data had been collected. And once you have that certainty, the logic keeps compounding. If every train is identical, running the same route, carrying the same cargo, on track with no interference from anything else, then the driver's job stops being a craft and starts being a procedure. And procedures can be automated. That is exactly what happened. After more than a decade of development and testing, one of the major ore operators put a loaded train on the main line in July 2018, with nobody in the cab at all. 3 locomotives, 28,000 tons, more than 280 kilometers from mine to port, monitored by controllers sitting in an office in Perth, 1,500 kilometers away. Within a year, the whole network was running that way. Roughly 200 locomotives and dozens of trains a day, on nearly 2,000 kilometers of track, operated by a system that a company executive once described as the largest robot in the world. It cost close to $1 billion to build. On a closed network hauling one commodity, that money pays itself back. On a network that carries everything for everyone, it would not even be a starting point. And there is a darker demonstration of the same principle, which happened on those same lines a few months after the first driverless run. A loaded ore train stopped on the main line one night in November 2018. The driver climbed down to inspect a problem with one of the wagons. While he was on the ground, the train started rolling. It kept rolling for 92 kilometers, picking up speed through the dark with nobody aboard and no way to stop it from inside. The remote operations center made a decision that no American dispatcher would ever be able to make. They threw a set of points and deliberately put the entire train on the ground. The wreck destroyed more than a kilometer of track and hundreds of wagons. Nobody was hurt, and nobody could have been hurt because there was nothing out there to hit. That is the Pilbara model in a single sentence. When the system fails, it fails into empty desert. If you are finding this useful, take a second and subscribe. We cover railroad engineering, operations, and the history behind them every week. Now turn to the other side of the comparison, and the picture inverts completely. The American freight network was not designed, it accumulated. Track was laid across the continent over roughly 2 centuries by hundreds of competing companies, most of which no longer exist, along alignments chosen for reasons that stopped applying generations ago. Towns did not grow up next to the railroad by accident. In enormous stretches of the Midwest and West, the railroad came first, and the town was platted alongside it, streets running out from the tracks in a grid. That history is now physically embedded in the network, and you can count it. Federal records list roughly 212,000 places where a public or private road crosses a railroad at the same level. 212,000 points where a freight train and a person occupy the same square of ground at different moments in time. In a small town, one of those crossings may be the only connection between the 2 halves of the community, and when a train is stopped across it, the town is cut in half. This is not an abstract inconvenience. Federal investigators looking into train length found local officials describing exactly what happens. In one small Ohio community, residents reported more than 20 freight trains a day, including one nearly 3 miles long, capable of blocking 4 or 5 crossings at the same moment. A fire crew on the wrong side of that train does not have a detour. It has a wait. Over a 2-year period, the Federal Rail Regulator logged hundreds of formal complaints about blocked crossings. The railroad's response was, in its own terms, reasonable. Longer trains mean fewer trains, and fewer trains mean fewer blockages. Local officials answered with the obvious rebuttal. Fewer, yes, but longer. And a crossing blocked for 20 minutes is not 4 crossings blocked for 5. That same federal review found something else worth sitting with. Average train length across the major carriers had grown by around a quarter in roughly a decade, with individual trains running to 3 miles on some routes. And the agencies responsible for safety were not systematically collecting data on what that change was doing. So here is the third constraint, and it is the one that has nothing to do with steel. Length is not just an engineering variable in America. It is a negotiation with everyone who lives along the line. Then there is the traffic the network has to share itself with. Long-distance passenger trains in the United States run almost entirely on track owned by the freight railroads. That arrangement was never comfortable, and it gets less comfortable as freight trains get longer. A passenger train needs to overtake or pass a freight, which means the freight has to be tucked into a siding, and a siding built to hold a train of a certain length in 1950 does not stretch. When a train is too long for every siding on its subdivision, the entire logic of dispatching changes. The long train can no longer be the one that yields. Everything else has to move around it. One oversized consist can reorganize the traffic pattern of a whole corridor. And this is where the comparison finally becomes clear, because it is not really about geography at all. It is about sequence. In Australia, the infrastructure came first. Heavier rail, longer loops, broader curves, purpose-built signaling. No crossings. Then, and only then, the trains got longer. The railroad was built to accept the trains it would eventually run. In the United States, the sequence ran backward. Beginning in the 1990s and accelerating through the following decades, the major carriers adopted an operating philosophy built around running fewer trains, making each one longer, holding them to strict schedules, and stripping out any cost that did not directly move freight. Financially, it worked. Operating costs fell, margins improved, and the markets rewarded it. But the trains got longer on the network that already existed. The sidings did not get longer. The crossings did not go away. The crews got smaller. The infrastructure was asked to absorb a change it had never been designed for, and it is still absorbing it. That is the honest answer to the question in the title. Not that American railroaders are less capable, or American locomotives less powerful, or American regulators more timid. It is that Australia's ore railways were designed around one commodity, one customer, one landscape, and one destination. And America's railroads were designed around nobody in particular and everybody at once. An ore line answers to a mine. An American main line answers to a chemical plant in Louisiana, a grain elevator in Kansas, a port in California, a passenger service that runs 3 times a week, and a town council that would like the crossing on Main Street cleared before school lets out. Could it be done? On a single dedicated corridor, engineered from scratch, with grade separations instead of crossings and no shared traffic? Yes. The physics would cooperate. The technology exists and has been proven. Something loosely resembling it already runs on the coal routes of the northern plains, where long uniform trains carry a single commodity over long distances. But building a true 4-mile railroad through the existing American landscape would mean acquiring right-of-way through country that has been settled for a century and a half, eliminating hundreds of crossings per corridor, separating freight from passengers, and getting the agreement of every county and municipality along the route. That is not an engineering project. It is a generational political one, and it would be paid for by shareholders who measure success in quarterly results. So the record stands, and it will probably keep standing. Not because nobody can beat it, but because the only places where you could safely beat it are places where almost nobody lives. The next time you sit at a crossing gate and watch a freight train grind past, count the cars if you have the patience. Notice how the load changes. A tank car, then a string of empties, then containers, then something heavy enough to make the rail flex under it. Every one of those cars is going somewhere different, for someone different, and every coupler between them is doing math you cannot see. That variety is the reason the train in front of you is a mile long instead of 4. It is also the reason the network exists at all. Australia built a railroad to solve one problem, and solved it perfectly. America built a railroad to solve every problem and has been living with the compromise ever since.